October 20th, 2025. In the span of just 14 minutes, the digital backbone of the modern web completely fractured. Over 17 million error reports flooded monitoring dashboards worldwide. Slack stopped delivering messages. Netflix streams buffered into oblivion. Atlassian's entire enterprise suite went dark. If you were on the internet that day, you felt it. But the scariest part, this wasn't a cyber attack, it wasn't a severed underwater cable, and it wasn't a massive hardware failure. It was a flawless execution of a perfectly flawed system design. Today, we are breaking down the largest cloud infrastructure failure of the decade, the collapse of AWS East 1, and how a single back-end bottleneck brought down the internet. To understand the collapse, you have to understand the architecture. Amazon Web Services is divided into global regions, but US East 1 in Northern Virginia is the mothership. It is the oldest, largest, and most heavily utilized data center in the world. At the heart of this region sits DynamoDB, Amazon's flagship, highly scalable, NoSQL database. When companies need single-digit millisecond performance at any scale, they use Dynamo. In distributed systems, an architecture is divided into two parts. First, the data plane, the actual servers reading and writing your data. Second, the control plane, the management layer that handles routing, metadata, and automated DNS. The golden rule of back-end engineering is that the data plane must survive even if the control plane goes down. But on October 20th, that rule was broken. At 9:15 a.m., an automated background process began updating routing tables within the DynamoDB control plane. It was standard maintenance, but a latent bug in the deployment code caused a fraction of the DNS metadata servers to briefly pause. In a microservices architecture, a pause is deadly. When the client applications couldn't reach the metadata servers, they did what they were programmed to do. They retried. Millions of automated systems instantly sent retry requests, overwhelming the remaining healthy servers. This is a classic system design nightmare, known as a thundering herd problem. The servers couldn't handle the exponential spike in traffic, so they crashed. Within minutes, the entire automated DNS management system for DynamoDB in US East 1 was completely paralyzed. The traffic cops were gone, and the requests were piling up by the billions. If this failure had stayed contained to Northern Virginia, it would have been a bad day for US East 1, but not a global catastrophe. This brings us to the concept of the blast radius. In cloud architecture, a blast radius is the maximum impact a single failure can have. Engineers design regions to be completely isolated, but there was a hidden dependency. Global services, like Amazon's identity and access management, IAM, heavily relied on the US East 1 DynamoDB endpoint for cross-region replication. When US East 1 failed, the IAM authentication system began throwing errors globally. Without authentication, servers in Europe couldn't talk to servers in Asia. Databases couldn't verify credentials. A localized bottleneck had triggered a cascading failure across the entire planet. The isolation was an illusion. It took engineers 15 brutal hours to manually throttle the retry storms, reboot the control plane, and bring the internet back to life. So how do we prevent this? The 2025 collapse forced a massive pivot in back-end engineering. Today, elite system architects no longer rely purely on regional isolation. They build cell-based architectures, creating isolated bulkheads within a single region so that a failure in one cell cannot mathematically propagate to another. They ruthlessly decouple the control plane from the data plane. The internet didn't break because of hardware. It broke because of interconnected dependencies. Infrastructure rarely fails. Control does. If you want to stop thinking like a junior developer and truly master the system design behind the world's biggest tech, hit that subscribe button. This is the Byte Thesis, and I'll see you in the next architecture breakdown.